Okay, let's get started. So I've put up the homework that's due on Wednesday, where we're going to finish up this first chapter on group theory. And then we're going to take a little time away from group theory and enter into the theory of vector spaces over general fields. So you've probably studied vector spaces over the real and complex numbers. We're going to study them a little bit more abstractly and do linear algebra in its full level of generality. And then we're going to return to do more on groups. So let me remember where Peter left you last time. We have this wonderful group, which is the integers under addition. That's our basic group. And we identified all the subgroups have the form n times the integers, where n is some integer greater than or equal to 0. So the multiples of some fixed integer. That's what we showed way back when we did the structure of this group. Remember, we used the Euclidean algorithm to prove that. And last time, Peter associated to every subgroup so this is our subgroup H. This is our group G. Each H in G. A new group, which he denoted Z mod NZ. So that's notation that's due to Gauss. So this would be called Z mod N. This notation in this group was defined on the first sentence of Gauss's great book, the Disquisitiones Arithmeticae, published in 1801, where this is the notation mod n comes from the Latin word modulus. The Disquisitiones is written in Latin. If I can get the first 2 pages from you from Houghton Library, I'll print them out and distribute. They're a précis of mathematical writing. And this new group, Z mod NZ, consists of the classes of integers where you only keep track of their remainder after division by n. So we have elements a bar in Z mod NZ, and a bar depends on the remainder of the integer a after division by n. So in particular, if a and b are integers, we have a bar equal to b bar, or as Gauss would write it, a congruent to b mod n. That's Gauss's notation. We'd say a bar is equal to b bar in the group Z mod NZ if and only if n divides a minus b. And so in particular, this new group, which only depends on the remainder, has only n elements in it. So this new group, you could say, consists of the elements 0 bar, 1 bar, 2 bar, up to n minus 1 bar, because those are the only things that are possible remainders. That's the group Z mod NZ. And the addition law is by adding 2 things in the integers and then calculating the remainder after division by n. So a bar plus b bar in Z mod NZ is equal to a plus b bar. Namely, add them in the integers. This is in Z, and then take the remainder after reducing mod n. And this gives the structure of a group on this set of n elements. And in fact, it's a cyclic group of order n generated by the class 1 bar. Because if you take 1 bar and you add it to itself, you get 2 bar. And then if you add 1 bar, you get 3 bar. And you add another 1, you get 4 bar. And you get up to n minus 1 bar. And then you add 1 to that, you get back to the identity element. So this gives another description of a cyclic group of order n. Remember, we claimed that there was 1 for each value n. This is the notation I'll use for a cyclic group of order n. It has the advantage that it not only is a cyclic group, but it has a natural generator, 1 bar. Just like the integers are a cyclic group with a natural generator, 1. This is an infinite cyclic group. This is a finite cyclic group of every order n. Moreover, we have a natural group homomorphism, f, from Z to Z mod nz, which takes the class of A to the class of A bar, i.e. A mod n. The remainder of A after division by n. And this is a group homomorphism. Which is surjective, because every class in this group is the remainder of something, surjective with kernel nz. Namely, the things that go to 0 bar are exactly the things divisible by n. So there's our subgroup. So to recapitulate what Peter did last time, and this is a great construction of Gauss's, which is the first example of this in the literature in 1801, before Galois had invented the general notion of a group, associated to each subgroup of the integers under addition, we construct a new group which is called the quotient group. We're going to do that more generally this time. The quotient group, such that there is a surjective homomorphism from the group to the quotient group with kernel the subgroup. Okay? Now, this is a much richer case than the average group. And the reason it's a richer case, and Peter went into this a little bit last time and we'll return to it, is that the integers have a much richer structure than just addition. Right? The integers also can have the product structure multiplication. Namely, the integers not only form a group under addition, they form a ring. So this also have the operation times. And when you have both a group addition and a multiplication structure, and they're suitably compatible, that's what we call a ring. And we're going to get to that, I promise you, this term. And in fact, this quotient group also has the structure of a ring. You can multiply remainders, and it's still compatible. Namely, you can define A bar times B bar by taking A times B in the integers and then taking its remainder. And that's a well-defined multiplication. So this is not just a finite cyclic group of order n, but it also allows you to multiply elements in it. That's a remarkable property. And most of the disquisitiones, in fact, one might say all of the disquisitiones, is concerned with the properties of those finite rings. Quadratic reciprocity theorem, the quartic reciprocity, all these great results that Gauss discovered are about the properties of this finite ring. And Peter introduced you last time to another thing. You see, if you have a ring, and I'm just going to say this very briefly, it's not necessary right now. So you have it's a group under plus with an origin, and then there's a times operation with an identity element 1, but not necessarily inverses. For example, 0 has no inverse. You can't multiply anything by 0 and get to 1. Nonetheless, you get a subset of the ring called R star, which is sometimes called the units of the ring, which is the set of elements A and R such that there exists a B such that AB is equal to 1. So they're the elements which have multiplicative inverses. Everything has an additive inverse. Now that can be a rather small, and this is another group. So ring is a group under addition, and you get a second group from a ring, which is the unit group, which is a group under multiplication. And it can be a rather small group. For example, this is the most famous ring of them all, the integers. All rings are modeled on the integers. If you ask yourself, what is the multiplicative group associated to the integers, namely which integers have multiplicative inverses, the answer is very simple. Just +1 and -1. There is no multiplicative inverse for 2 because 1/2 is not an integer. So for this ring, we would find that the multiplicative group here is just the group on 2 elements plus or minus 1. It's a kind of a stupid group, but there it is. On the other hand, as Peter pointed out, these finite rings have very interesting multiplicative groups. Very interesting. And we're going to get into that later when we do the ring theory. And Gauss was the first person to work out the structure of the multiplicative group of units in those rings. But right now, for this point of view of this lecture, it's only important that we inherit the additive group structure and that we have this additive group homomorphism. Before I go any further, are there questions on this construction? Because it's very basic. It's the model for what we're going to follow when we do a quotient group in general. Okay. So let me be a little bit more general than this. Now this is a particularly simple group. As I said to you, this is an abelian group. So we have to pay attention and see what properties are we really using of these subgroups when we construct this quotient group. Can we do it for any subgroup, or is there some peculiar property of the subgroup that we need? So let me start off in a simple situation where the subgroup is defined by a group homomorphism. By the way, these classes in Z mod NZ are just the cosets of this subgroup. Represent the cosets of NZ, the distinct cosets. So the quotient group is the set of cosets of the subgroup. And yet we're able to give a multiplication on it. So that's going to be our question. When can we put a group structure on the set of all cosets AH for a subgroup H in G? We always get if we have a subgroup, we get a set. It's set of cosets. And we've seen that that gives a partition of the group. Here's our group. Here's H. Here's AH. Here's BH. So we get a nice partition of the group into cosets. So this set of cosets is a nice set. When can we get a group structure on it? So one case, case 1. Suppose H is equal to the kernel of a homomorphism, F, from G to G prime. That's one way we get subgroups. Then the set of cosets AH is in bijection with what? How do we get a coset out of a homomorphism? You remember that? H was the kernel of it. What are the other cosets? The fibers, exactly right. Namely, we had a map here from G to G prime. It needn't be a surjective map, but above each point in G prime, A bar, we have the fiber, which is an entire coset of the kernel. And we had another point here, B bar, you got its fiber. All the things mapping to B bar, right? So the set of cosets are the fibers of the map. So therefore, they can be identified bijectively with the points A bar in the image, which is contained in G prime. Correct? Each coset corresponds bijectively to a point in the image, which is some little thing in here. Image of F. And the image of a homomorphism is what? Among other things. It's a subgroup. But the image of F is a subgroup. It's stable under multiplication in G prime of G prime. Therefore, since the set of cosets is in bijection with the set of the image, and we have a group structure on the set, on the image set, that gives us a group structure on the set of cosets, right? Good. So we transfer, sometimes mathematicians, if they wanted to be sophisticated, would say we transport the structure of the image onto the set of cosets. Or if you wanted to be even more sophisticated, you say it in French. Because that's a favorite expression of Bourbaki that wrote up a lot of 20th century mathematics. You'd say, par transport de structure, on a une structure de groupe sur l'ensemble des cosets. Okay, coset is what in French? Coset? Did I do that right? Not bad. You must learn French. If you aspire to be a mathematician, you want to say things precisely, they must be said in French. English is, of course, the worldwide language of mathematics and science nowadays, and has become even more so in the last 25 years. But there's certain types of mathematics you can only say in French. So we say par transport de structure. We get a group structure on the set, and we'll call that set G mod H of cosets. And the group structure has the following form. When you multiply the coset AH by the coset BH, then I claim that the answer is, which coset is the product? It's just the coset of AB times H. Why? Because if I want to figure out how to multiply this coset by this coset, I have to figure out how to multiply A bar by B bar. Right? That's the multiplication law I'm going to use, the multiplication law in G prime. So what is A bar times B bar? Well, it's the bar of something because it's in the image. What is it the bar of? Well, we figure this out by writing A bar as F of A and writing B bar as F of B, and then using the fact that F is a homomorphism. And then this number is just what we would call AB bar. So the product of the image element A bar by the image element B bar is the bar of AB, where this multiplication takes place in G. So that's what I mean. So when you want to multiply two cosets, you just take an element A in one of them, you take an element in B in the other, you take the product of those elements, and you take its coset. And moreover, this makes the map F, new map, let's call it capital F, from G to G mod H, taking A to the coset AH, a group homomorphism. A surjective group homomorphism. Because this is the multiplication law. It's inherited from the multiplication law in G. So if we have a group homomorphism and we let H be the kernel, then by using the multiplication on the image, we can make the set of cosets, which is denoted like this, into a group which is called the quotient group. And the multiplication law looks like this. And if you think about what we did for Z mod NZ, it's a similar multiplication law. Yeah, good.
When you were saying that the map little f creates a group on G, I think?
No. There's always a group on big G. And there's a group on G prime. And there's a homomorphism between them. Now, there's a group structure on the image because that we agreed was a subgroup of G prime. Okay. Now, the cosets are identified bijectively one-to-one with the points in the image. Therefore, it tells us how to multiply one coset by another coset and get a third coset. That's different than multiplying elements in G. We're multiplying elements of a different set. And the multiplication law is this. By inheriting the structure of the group on the image. Okay, now, this worked pretty well. Let's forget that we had a homomorphism. All right, so try better. Better. Let H in G be any subgroup. Okay. Let the cosets G mod H be the set of all cosets AH. That's a good set. We've defined that for any subgroup now. We know what a coset is. That gives a partition of G. Okay, define a group structure on G mod H by setting the product A times H times the coset B times H to be the coset of AB times H. That's what we did here. That's what worked. Hold on. So I'm now going to try, maybe I should say try to define a group structure on the set of cosets by that law. That's what worked for us here. If we multiply two cosets here, we got a third coset. Why don't we try it here? Okay. Now, I said try. This fails. It fails. I'm going to show you now it fails. So you shouldn't get too optimistic, but you should always try. You never get anything in math by just saying, well, everyone's always done it that way, I'll do it this way. Right? You have to try something else. So the reason it fails is the following. You have to ask, before you get the group structure and everything, by the way, you have to check that this is associative. You have to figure out what the identity element, by the way, what's the identity element in the quotient group? The identity element? Identity element has to be the image of the identity under this homomorphism is equal to E bar, which is the coset of E, which is just the coset H. That's the only distinguished coset you have. So this becomes the identity element in the quotient group. How about the inverse element? Now that we know the inverse, what's the inverse of the coset AH? What could it be? The coset of A inverse. See, because A times A inverse is the identity element. So if I took inverse, it would be AH inverse is A inverse H. But those are all details. I mean, first you have to have a multiplication law before you get the identity and the inverse and associative and this and that and the other thing. So what would be the problem with this as a multiplication law? What is the problem with this as a multiplication law? It looks pretty good. I tell you how to multiply this coset by this coset. I tell you it's that coset. Yeah?
Well, if AH is the same as like some CH.
Ah, good. Exactly. Namely, the question is this well defined? Because the coset is not uniquely written as AH. Namely, if AH is equal to A prime H, if A and A prime are in the same coset, and BH is equal to B prime H, is ABH equal to A prime B prime H? Namely, if we're saying that this coset times this coset is this coset, we better make sure that doesn't depend on what representative we've chosen for the coset. And there's no unique way of writing a non-trivial coset. You just have to pick something in it. Here we called it AH because the element A was in it. But we could have had another element A prime in it and written it as A prime H. And if we say that this multiplication law depends only on the coset, we better make sure that no matter what representative we choose, it works. Now, in this case, it has to work because it's the law on the image. All right, but I'm going to show you that it doesn't always work. So the answer to this first question is 1, okay, if H is equal to the kernel of a homomorphism from G to G prime. There we go. 2, not in general. Suppose AH A inverse is not equal to H, i.e. AH is not equal to HA. Okay, for some element in the group A, for some A, the conjugate of H is not equal to itself as a set. Then I'm going to show you that this definition encounters some serious problems. Some serious problems. Because let's multiply the coset AH by the coset A inverse H. Under this definition, it would get me what coset? It would get me the coset H, because A times A inverse is E. So this would be EH is equal to H under this definition. Now, if you think about this requirement, this says, since this would be true for any A prime and AH, and this would be true for any B prime and BH, it says that this definition will only work if the product of anything in here times the product of anything in here is in this coset. Right? Because I could take anything here as my A prime, and anything here as my B prime, and then I better make sure that A prime, B prime is in this coset. In other words, that this coset is equal to that coset. So, if I were going to use this as my multiplication law, I would have to say that anything in here times anything in here was in H. Right? Now I'm going to show you that's false. That's false. So that definition is out the window. Can someone give me a product of something in here times something in here which is not in H? Yeah, Emily. Okay, so this says here that there exists an element H in H such that A inverse is not in H. Right? That's this statement here. There exists one element in here such that when I conjugate it, I get out of H. Okay? So I take, as a suggestion, the element AH in here, right? And I take the element in here, A inverse times E, which is certainly good. And I take their product, and I get AH A inverse, which is not in H. By my hypothesis. So, if I have a subgroup which has the property that some conjugate leaves the subgroup, I can forget about this definition because it's not well defined. Before I even checked any product properties of it, it's not even a well-defined multiplication. It's not true that the product of anything in this coset times the product of anything in this coset is in here. Okay, now how come, now we have to sort of sort. How come it worked in one, but not in general? What was so special about the H that were in one? Yeah. It's abelian. Not quite, but close. It's a normal subgroup. Namely, the kernel of a homomorphism has the property that AH, A inverse, is equal to H for all A in G. That's what we called a normal, it's Galois terminology, subgroup. Because if you apply the homomorphism to anything of the form AH A inverse, using the fact that f of h is the identity, you get f of a times f of the identity times f of a inverse. And f of a inverse is the same as f of a inverse, so the product of those things is the identity. And you're still in H. You're still in the kernel. The kernel is not an arbitrary subgroup. It's a normal subgroup. And so, since it worked in this case, we might see, and it doesn't work in general, if this happens, we might see if normality is what we need. Three, assume that H is normal in G. So, AH A inverse is equal to H for all A in G. In other words, we could write this as AH is equal to HA as sets. Okay? Doesn't mean that A commutes with everything in H. It means that if you have an element in H, that AH can be written as some H prime A or H prime in H. Okay? It just preserves it as a set. It doesn't commute with everything in H. Okay? Now, in this case, the naive multiplication law on cosets, and by the naive multiplication law on cosets, I'm going to violate a cinematic principle here. I mean this thing, which is in a different quadrant. Apologies. Okay. The naive multiplication law on cosets actually works, is well defined, and defines a group structure on G mod H, on the set of cosets. Now, that wasn't obvious from 2. All we said was if this didn't work, then you didn't get a group from the naive multiplication law. So we still have something to check. Namely, we just said, well, this didn't work. Let's assume this works. Now everything's OK. We have to check that. Correct? So let's check it. We have to show that if you take all things in this coset and you multiply them by all things in this coset, you get a coset, namely this coset. Check. Well, suppose we multiply AH by BH in this. And this means, by this I mean take any element in here and multiply it by any element in there as sets. Let's just calculate the set by calculating the set of all products. So this means everything of the form AH, B, H prime in G. That's that set. Okay, where H is anything in H and H prime is anything in H. That's what I mean. Take all things in this set and take all products with things in this set. Now, how do we calculate that? Well, first of all, we rewrite this AH as HA because this set is the same as this set, right? Okay? Now I claim that that's the same set as H, A, B, H by associativity. Okay? I mean, this is the set of all things H, A, B, H prime. So associate AB, it's a set of all things H, AB, H prime by associativity. And now I use the normality of H once again to rewrite this as AB times H by normality. Now this time with respect to the element AB, not with respect to the element A. This is by normality. Because for any element A in G, this is the case. We didn't just assume it for the unique element A. To be a normal subgroup, it has to be for any element. And now we look at this and say, well, my gosh, if I take a product of anything in H times anything in H, what do I get? Something in H, because H is a subgroup. So this is the same thing as AB times H, as H is a subgroup. And that shows that as a set, if you take the product of anything in this coset times anything in this coset, you get the elements of this coset. And that's what we needed for this multiplication to be well defined. Okay, so this is something you must go through carefully yourself. I can do it at the board 50 times, but the difference is taking products of sets and products of elements. This looks so good. But that's because I've got a preferential writing for this coset. Don't ever be deceived into thinking you have a good way of writing down a coset. You don't. Okay? The integers mod n are very bizarre in that you have rather natural representatives from the cosets, the numbers from 1 to n. But you could have also taken the numbers from 0 to minus n. What's so good about positive numbers? Or you could have gone from minus n over 2 to plus n over 2. There are all kinds of ways you could have represented the cosets. And even taking the numbers from 1 to n, which looks so great, when you add 2 of them, you overflow and you have to go back. Right? So you don't have natural representatives. And that's why this kind of beautiful looking multiplication is just wrong in general. However, the miracle of normality is that it actually works out to be okay. It defines a group structure on G mod H with identity, the coset EH, and inverses. AH inverse is equal to the coset A inverse H. So that you have to check. So that's the answer in general. You can make a group structure on the set of all cosets for a subgroup if and only if H is normal. If and only if H is a normal subgroup. Otherwise, there's no natural group structure. There may be ways you can put a group structure on the set, but not in some natural way that reflects the addition law in G. Now, let's go a little further on this. Because we have not only a group structure on the set of cosets, we get a natural homomorphism. So, if H is normal in G, get a group structure on G mod H, the quotient group, and a surjective homomorphism, group homomorphism, F from G to G mod H, that takes the element A into its coset. That's surjective because every coset is the coset of something. And it's a homomorphism because we've defined the group law in this way. And it's a homomorphism because f of A times f of B is the coset of ABH, which is f of AB. And one more thing, since it's surjective, we know what the image of this map is. What is the kernel of this map? The kernel is the things that map to the identity in here. The identity is the coset EH. What elements in G map to the coset of E? Yeah. The elements of H. The coset of E consists of the elements in H. So the elements in G that map to the identity E prime, F inverse of EH, which is the coset H. And that, finally, is the answer to a question that was asked a week ago. Every group homomorphism has as its kernel a normal subgroup. Conversely, every normal subgroup is the kernel of a group homomorphism. Here it is. You have a normal subgroup. Here's a group homomorphism which exhibits it as a kernel. Let's put that down because it's so important. Corollary. Every normal subgroup H of G is the kernel of a group homomorphism. It's the only way to get normal subgroups. With image, well, yeah, it's the kernel of a group homomorphism. All right. Now, the final result I'm going to deal with today is more or less tautological, but it's got a fancy name. It's called the first isomorphism theory of group theory. I don't know. These names are idiotic. The fundamental theorem of algebra is not a theorem in algebra at all. It's a theorem in complex analysis. But never mind. We're going to skip the pretentiousness of this name. But it's a nice result. And it somehow ties the kernels and everything we've been working together. All right, so this is called the isomorphism theorem. You'll see where the isomorphism is. It's tautological, as all good theorems are. Namely, you've built up enough ammunition, so you just kill the theorem right there. So we've built up enough ammunition, just kill this. It says if f from G to G prime is a surjective group homomorphism with kernel H, and here's an example of one. Here's a surjective group homomorphism with kernel H, namely to G mod H. Then F induces an isomorphism, which I'll call F bar, from G mod H to G prime. Sometimes isomorphisms are denoted like that. So an invertible homomorphism, an isomorphism of groups. So if you have a surjective homomorphism and you know the kernel, you know the image as a group. The image is exactly the group structure on this quotient group. You can construct the image from the kernel. And this map, F bar, of the coset AH is equal to, by definition, F of A. And you have to check that that's well defined. Namely, that the value of F is independent on what coset representative I choose. But that's just because the kernel of F is H. So F of A is equal to F of A prime if A prime is another element in AH. That's just because H is the kernel. And you have to check that this is an isomorphism. So that shows that it's a well-defined map. Then you have to check that it's a group homomorphism. Well, that's because our multiplication law in the quotient group is that AH times BH is ABH. So you check that using the multiplication law in the quotient group, this is actually a homomorphism. It's surjective because the original thing was surjective. So if you wanted to hit something in G prime, you'd find an A in G that mapped to it, because this is assumed surjective, and you take the image of that coset, and you hit your element in G prime. One moment. And it has no kernel, because the original, well, it has a trivial kernel, because the original kernel was the subgroup H, but H has been collapsed down to the identity in this group. So the only things that map to the identity in G prime are in the coset H, which is the identity element of this group. So I've got a construction that somehow collapses the kernel down and makes a new group where now I have a trivial kernel and the same essential homomorphism. I'm sorry, I just wanted to get all that out. Now, let's go back and get the question.
Okay, what exactly do you mean by
Induces an isomorphism. Namely, this map gives another group homomorphism. This is the induced homomorphism. It's sort of so tautological that the definition of F bar follows from the definition of F. That's what I mean by induces A. And then the key thing is that it's an isomorphism. Both surjective, which the original one was, but now with trivial kernel. 1-to-1, because I've collapsed the kernel down in this quotient group process. So anytime I have a surjective homomorphism, I can turn it into an isomorphism by going to the quotient group here. Yeah?
This might be a silly question, but can you always define the quotient group of G?
We can define G mod H, a quotient group on G, for any subgroup that's normal. That's what we first checked. But the beautiful thing is that the kernel of any homomorphism is a normal subgroup. So from this definition, from the fact that H is normal in G, I go construct G mod H as a group. And then the theorem says that this map which is not an isomorphism induces an isomorphism on the quotient group. Okay? It's not a deep result because we've done all the work. Namely, all the work is figuring out which subgroups we can associate quotient groups to, and what the multiplication is in the quotient group, and defining a map from G to G mod H like this. Now, Peter would say that a better way to write this is to take the original homomorphism like this, to construct our nice homomorphism surjective to G mod H like this, where H is the kernel. So this would be a surjective map, right? So this we could construct, let's call this map capital F. So we construct F like this. And if you think about the construction of this map F bar, it just says that we can construct a map up here, F bar, such that the composition of these two maps is this map. Because this map capital F takes A to the coset AH, and then F bar takes the coset AH to what F did to A. So Peter would say that a better way of stating the isomorphism theorem is to say that any homomorphism factors through the quotient group. Okay? The quotient, this canonical homomorphism by the kernel. So not only, remember that when you construct the group structure on G mod H, you're not just constructing a new group. You're constructing a new group that comes with a map. And the isomorphism theorem says that you can factor a homomorphism through that map. When you get on and you do category theory, where the only thing you do is write down little things and arrows between them, this will be a useful way of stating it. Okay? But this is a good way to think about it, that you convert a homomorphism into an isomorphism via the quotient construction. Now I'm going to give you a little bit of notation now, and to give you also a little bit of warning about it. So I'm going to tell you what an exact sequence of groups is. Well, actually, I'm going to tell you what a short exact sequence of groups is. So exact sequences is a notation that comes up in homological algebra. When you take a course in algebraic topology, you'll see 1,000,001 exact sequences. The notation, the actual terminology exact sequence was invented by Eilenberg and MacLean in the 40s after much thought as to what the heck they should call it. An short exact sequence of groups is a diagram of 5 groups. You start off with the identity group. That's called the identity group, 1. Then you have a subgroup H. Then you have a group G. Then you have a group G prime. And then you have another group 1. This is and everything in this is a group homomorphism. F and G are group homomorphisms. So are these maps. I mean, any group, you can always map the identity into a group. That's a group homomorphism. One goes to the identity. If you map everything in G prime to the identity element in this group, that's a group homomorphism too. Okay? They're group homomorphisms. G of H has to be the kernel of F. That's what it means to be a short exact sequence of groups. So that it identifies, and F is surjective. And H and G is injective. Sorry, group homomorphisms. Let me write this again so I get it actually right. G is injective. G is 1, 2, 1. And F is onto. So this is a surjection. So G prime is the image. This is an injection, so it identifies H with the kernel of F. So that G is built out of these two groups, H and G prime. So G prime would be identified, by the way, by the isomorphism theorem with G mod H. Because this would be a homomorphism with kernel H and image G prime. So by the isomorphism theorem, it identifies them. So this is a way of saying that a group is built out of two smaller objects, an image group and a kernel group. It's not important that you get all this now, but you're going to see it a million times. And here's the warning. Do not think that because you know H and G prime, you know G. Note, the inputs H and G prime do not determine the group G. And I'm going to give you two examples of it, so you remember this for all time. Take the group, the symmetric group on 3 letters. That has as normal subgroup the alternating group on 3 letters. The quotient group is the group plus or minus 1 of 2 elements. The sign map. This is the sign map. This is the obvious inclusion. That's an exact sequence of groups. Here's a group with 6 elements. The subgroup has 3 elements. The quotient group has 2 elements. Okay? I'm going to write you down another exact sequence. The cyclic group of order 6 maps to the cyclic group of order 2 by taking a congruence mod 6 and just looking at it mod 2. So the odd elements in here go to 1 here, and the even elements mod 6 go to 2, go to 0. The kernel is the cyclic group of order 3. That's another exact sequence. So this takes A to A mod 2, which is well defined. And this Z mod 3Z is really the elements divisible by 2, 2Z mod 6Z. It's the same group. Okay, those are 2 exact sequences if you think about them. There's a kernel, there's an image. Okay, this group is isomorphic to this group because all groups of order 3 are cyclic. We proved that for groups of prime order, right? This group is isomorphic to this group because all groups of order 2 are cyclic, and therefore they're equal. But this group is not the same as this group because this is an abelian group of order 6, and this is non-abelian. So even though you can sometimes break a group up into a subgroup and a quotient group, and you've learned something by decomposing it that way, the pieces at the ends do not determine necessarily the group in the middle. There's more information you need to put these 2 groups together into this group or to this group to say which one you're getting. Yeah?
I'm not sure I understand what the ones on your end.
Those ones are just the trivial group. Sorry, suppose I wrote it like this. What they mean to indicate in this exact sequence terminology is that this map is an inclusion and this map is onto. If I could say it the following way, to say this map is an inclusion is to say that the image of this map is the kernel of the next map. That's how it comes up as an exact sequence. An exact sequence means the image is the kernel of the next map. So the image of this is just E. So if that's the kernel of G, that says this map is an injection because its kernel is trivial. And likewise, if this map is onto, then it says that the image of this map should be the kernel of this map. Well, this map takes everything to the identity element. So its kernel is everything. But usually you don't indicate the group E, but you just write it as the group 1 like this. This is just notation that signifies that this group is built out of this subgroup and this quotient group. Okay? But those of you who will see this in algebraic topology courses should at least see what it means in group theory. We're not going to use this notation. You can put it away. But just remember when you encounter it that you don't get the group in the middle from the normal subgroup and the quotient group. Okay, Wednesday.